In the first chapter, we'll be looking at how we can actually represent the things we're measuring in terms of SI units and prefixes. We'll be looking at a special question that usually comes out. We'll talk about what we should actually use to measure things, and we will also be talking about these things concerning scalar and vector. Right, so let's hit the first part, which is about how do I represent all these physical quantities. So when we do talk about physical quantities, we're saying that, hey, there are these things which I can measure. These are known as quantities. Let's start with things, the basic ones, otherwise known as the base quantities. I like to think of it that these are the basic ones because from all of these basic quantities, we will then move on to things known as derived quantities. Now, the base quantities we're going to start off with would be things like length, time, mass, temperature, current, and amount of substance. But for now, let's just go with the first three, length, time, and mass. There are many ways to represent length. I could use yards, I could use inches, but we're going to use things called SI units. As such, when I look at length, I think in terms of meters. When I talk about time, the SI unit would be seconds. And if we're talking about mass, it's going to be kilogram, right? Now, I can use length and time to find other quantities like speed and so on and so forth. Those are derived. So let's say I want to look for something like speed. So what is the unit I use for speed? I will have to consider the fact that I know the formula for speed, and therefore I know that if I look at distance, I'm talking about length. So distance, the unit I would use on top, SI unit would be meters, and time would be seconds. This also gives me the SI unit that is required for this derived quantity. That's the reason why when we talk about density later on, we cannot use gram per cm cube, we have to use kg per meter cube, because these are the derived quantities and that's the SI unit I must consider. All right, now other than SI unit, we also realize that kilogram seems to be not just gram, but kilogram. Why do we use these things like K? What are these symbols over here? These over here are our prefixes. There's a list of prefixes that you must know, and they basically help us to represent really big or really small numbers. So let's list all the prefixes that you should know for examinations, starting from the biggest to the smallest. We have tera, we have gamma, mega, kilo, and now going small, deci, centi, milli, micro, this also known as mu, that's how you say the symbol, and finally nano. I always found it interesting that these are all the multiples of 3, but beyond here, that's where it gets smaller. What would it be? In some cases, you may need to know pico, which is 10 to the power of negative 12. Now, what could be asked of you in these cases? It could ask you to convert things, like if I want to go from km per hour and convert to meters per second, you need to know how to change km into meters using the correct prefix over here. One of the more common questions you usually see would be they ask you what would be the order of magnitude for diameter of Earth, diameter of human hair, and diameter of an atom. So these are the three things that you want to consider. So these are the three order of magnitudes for the diameter of Earth, diameter of human hair, and diameter of atom. So these are the three things that I would try to remember. If you're asking about like the actual size, this is what's going to be 10 gigameters, 0.1 mm, or 0.1 nanometer. Now let's cycle back to the up here. When we look at the base quantities, we know that length, time, and mass are base quantities. So the question would be, what do I use to measure these base quantities in the first place? So there are a couple of things to know for length and for time. Mass will be something that we see later on. In terms of length, this is the list of instruments that we could use. How they are arranged is basically as you go down this way, you have an increase in your precision, which means you're able to measure smaller divisions very, very accurately. And these are the common instruments you use. What about time? For time, we only think about two things. We would use either the digital stopwatch or we can use a pendulum. Digital stopwatch means I would use my timer. The issue with using a timer would be that I could have human response time error, right? Because there's only so fast I can press the thing, there's only so fast I can react to what I'm seeing. So to deal with that, you will need to take multiple readings and then find the average of all those readings. For pendulum, there's something that you'll touch again when you hit waves. You need to know that a pendulum is basically you measuring a period. And what is the definition of period? It's a time taken for one complete oscillation. Questions could include what would be the most suitable instrument to measure maybe the inner diameter of a test tube. Then you, oh, I got to use the digital calipers. Or I want to find um, the circumference of a tree trunk. Oh, then I'll use the measuring tape. So it's going to talk about suitability of the instrument. All right, so now that's done, we have to go to the final part, which is the difference between scalar and vector. Scalars and vectors would really just come down to another list that you must recall. But first, let's try to understand the difference between a scalar and a vector. So much like what we talked about over here, scalars and vectors are actually quantities. But the question is whether or not this quantity has a direction. That is why there's a difference between looking for distance and looking for displacement. Likewise, there's a difference between looking for speed and looking for velocity, because these two over here gives you one additional information, which is the direction. However, there are quantities which don't have direction. For example, if I think of time, there's no direction for time. If I think of mass, there is no direction for mass. So these are things you want to remember. Oh, what some more? We can talk about temperature. Yep, right? No direction. It's just a scalar. Now, you can imagine it's going to be pretty straightforward to add scalar values. Like, for example, if I have two boxes, right? Now, these two boxes, I'm telling you that the mass, this is 6 kg and this is 10 kg. It's easy to know, oh, what is the total of it? Well, I know I added up, it's 16 kg. But the problem is that when it comes to vectors, direction plays a part. So there are methods, not just addition and subtraction, there are methods we need to have to actually figure out what is the result of the vectors, where direction plays a part. So there are two methods we use. One is called the tip to toe method, and the other one is called the parallelogram method. So let me introduce one vector that looks like this, and another vector that looks like this. Okay, and let's try to solve it using these two methods. Okay, let's start first with the tip to toe method. Oops. Let me try to bring this down here. The tip to tail method really just means that um, so this is the tail and this is the tip. My tip must go to a tail. So we're trying to see where, if I can connect it, my connection will always be from one tip to the next tail. So let's bring this over here, tip to tail. So I'm asking, right, in the end, what's the result? Where did it go? So I'll say it went here and here. So basically start and end. So what's the general overall direction for this? It would look something like this, drawn with a double arrow to show resultant. So this is a parallel, sorry, this is the tip to tail method. How does the parallelogram method work? So for parallelogram method to work, usually we will try to arrange it such that they originate from the same point, something like this. Now, when that is done, I'm able to now imagine I want to complete a parallelogram. When you think of a parallelogram, right, things like these, all you're going to realize is that this and this is parallel, that and that is parallel, except that I'm starting with this and that, correct? So if these over here weren't available, let's see, can I erase it? If those weren't available, and I just am left with these two, I will need to try to complete the parallelogram by drawing the other two sides. So likewise, let's draw it for this one. Let me draw the blue such that it's the same direction, same length, and then after that over here, as the red, same direction, same length. And now that I got a parallelogram, I'm going to start from the originating part. I need to draw a diagonal across. Now, if I have two forces acting this way, one here, one there, the result has to be somewhere in between these two, right? So I'll go from the originating point over here and go to the opposite diagonal. Okay, now if you forgot or you just need an easy way of remembering, for parallelogram method, put it such a originate from the same point. After I draw it out, go from that original starting point to the opposite diagonal. And I will get something that looks similar to this. And as you can tell, these two methods will give me the same answer. The thing is that when you go on to the next chapter concerning dynamics, drawing it won't be just sketching. You need to be very accurate, showing exactly what is your scale and drawing it clearly. Right? But this is an introduction to the tip to tail and the parallelogram method. Now, let's check back before we hit before we hit 10, 11 minutes. Something just shifted. Are you able to do all of these? Are all of these things clear to you? If they are not, go back and watch one more time or contact me.